In this chapter, we're studying conditional probabilities, and we start off with a problem 41 on page 229. In genetics, a geneticist is studying two genes. Each gene can either be dominant or recessive. A sample of 100 individuals is categorized as follows. Here is your table of interest, and you will notice we have marginal totals on either side here, both row and column marginal totals, and they will help us calculate the conditional probabilities. Question A is, what is the probability in a randomly samples individual gene 1 is dominant? So we have here the probability of gene 1 given and is dominant. So a dominant gene 1. So from here we look at the probability of 80 divided by 100. That's the probability that gene 1 is dominant in this sample. What is the probability that in a randomly sampled individual gene 2 is dominant? Well, in this particular case, it's going to be, we look down the column of dominant for gene 2. This is gene 2, and we see that it's 70 divided by 100, which is about 70%. Now we come across a term that we have talked about in class called given. So this is the first event. So given that gene 1 is dominant, what is the probability that gene 2 is dominant? So we write it as the following. The probability of gene 2 dominant given gene 1 is dominant. And here we use the fact that we go, the given row in this case is dominant gene 1, which is going to be our denominator. In our numerator, it's where dominant is intersecting with dominant. So it's going to be 56 over 80 in this case. And again, it is 70% here. And then our final question is, two genes are said to be linked in equilibrium if the event that gene 1 is dominant is independent of the event gene 2 is dominant. Are these genes in linkage equilibrium? Well, in this case, the answer is yes, and the reason why is when we do the calculation of the AND statement, gene 1 dominant and gene 2 dominant, in the whole sample, we see that 56 divided by 100 is 0.56. And yes, they're independent linkage because guess what? This calculation makes sense because of the fact that when we multiply the probability of G1 dominant and G2 dominant, we just get the probability of G1 dominant times the probability of G2 dominant. And since those are equal, they are in fact independent. So now we're going to go to a different problem in the book where we are given problem 51 on page 230. Defective components. A lot of 10 components contains 3 defective items. If two components are drawn at random without replacement and tested, let A be the event that the first component drawn is defective, and B is the event that the second component is defective. So in this case, if we have 10 items, and I'm just going to represent them this way. So here I have 10 items, right? And in fact, of those 10 items, 3 of them, right, are defective, right? And so if 2 are drawn at random without replacement, so event A is the fact that we are drawing the first one out, and then we keep that one out of the mix, right? So the probability of A is nothing more than 3 divided by 10. That makes sense because I have 3 defectives and I have 10 components, so the first draw is in fact 3 divided by 10. Now I leave that one out and I'm left with, so this one is gone, and now I'm left with 9 components. 2 of them are defective. And we said event B is that the second component is defective. So now when we choose the second component defective, right, now this one is different because now it's 2 out of 9. So the probability, right, that A, given that A occurred, what is the probability of B is 2 divided by 9, right? And then finally we have the multiplication rule. Find the probability of A and B, which is just the multiplication of the first event, probability of A times the probability of B given A. So that's these two. And we end up with 1 over 15, which in this case is our final answer of 0.0667. Then part D is, are A and B independent? Well, no, they're conditional, obviously. But we could go through and show you that, in fact, they are not independent, because if they were independent, then we would get the probability of 0.09. But when we did probability of A and B, we got 0.0667. So these were a conditional scenario, a conditional event. So the conditional probabilities are used a lot in medical applications, and I wanted to show you a study in the 1970s using a contingency table. So we will go through this particular problem. In the 1970s, medical research was looking at the relation of blood types to cancers. One study was the following, found in Statistical Methods, 8th edition by William Crockton. In the study of the relationship between blood type and disease, a large sample of patients are examined to have peptic ulcers, gastric cancer, or free from these ailments. The following table, which does not include the AB blood type because it was just too small of numbers, are in the following table. So here's the blood type over here, right in this column. We have peptic ulcer, gastric cancer, no disease in total. On this side, of course, the blood types are going across the rows. So the question is what is the probability that a patient has cancer given that they have O blood? So gastric cancer is the question. And we can see that the way we look at it is the following. We look at the row of O, which is the given row. This is given. And we go within the row to see where the cancers are. And we have a ratio of 383 to 4258. In this case, it's approximately equal to 0.0899, which is about 9%. We look at the A category, A blood types, and we ask the same question. What is the probability that you have gastric cancer, given that you have A blood type? And again, we now look at what's given. Given is blood type A, and then we go in and we look at the gastric cancer. In this case, it's 416 divided by 3,720, which is equal to 0.112, or approximately 11.2%. So there is a slight difference, or there is a difference between blood type O and blood type A as far as gastric cancer is concerned, it appears. And then finally, in this example, what's the probability within this population to have type O blood and peptic ulcer? So now we're looking at the AND statement. And here we go inside the table where there's an intersection between peptic ulcer and O-type blood, which is 983 to the total sample. The AND includes everybody. And so when we do that ratio, we get 11.2%. Right? So for O-type blood, it's more common to have a peptic ulcer than gastric cancer. So that concludes our problems in Chapter 5.3 on conditional probabilities. Please review any information, or if you have questions, please bring them up in class.